We are going to cover the news vendor problem. What this is allowing us to determine how many items we should procure to maximize our profitability for a specified period of time. I have a few slides to show what it's all about, defining the problem statement, the math behind it, explaining what we're trying to do, and then an actual dive into the overall application. The specified period of time is important here. This is modeling for a very specific time period. It's not going to take into account your entire network. But for problems like newspaper sales, perishable items for maybe a grocery store sale, this is a great tool to help simulate what may or may not happen to maximize your overall profit. So what is the problem that we're trying to solve? We said the news vendor problem is what it is. So really what we're trying to determine is how many newspapers should be ordered to balance sort of our demand uncertainty, meaning what can we sell or what won't we sell? Really trying to make sure that we don't buy too much and eat the cost of excess inventory, because once we've sort of passed a news cycle, it's no longer necessary, or ordered too few of results, ultimately resulting in lost overall sales. Our overall objective, which we're not going to go into the code or how it was built, we could on another video, but for this purpose, just sort of understanding the problem and what we're trying to solve for, is we're going to build an application and Streamlit to solve the problem. Like I said, using one single period of inventory sales to sort of use as the model. It's not going to model the entire network or multiple periods. And then adding that sort of uncertainty within our Monte Carlo simulation and rolling the dice to see what may or may not happen. And ultimately, for a lot of this, is we're trying to determine what is our leftover inventory versus our stock out, and trying to make sure we manage it appropriately based on a certain probability that we made the right decision. So what does this really look like when we start to lay everything out in a table format? So here I try to lay out sort of historically what demand we've had for our products and the probability that demand would occur. I sampled sort of that over time. And then down below, you see the exact same sort of thing, demand in units and then probability. And let's say we can buy an item for $1 and then we sell it for maybe $1.50. And we want to, that only happens when we can procure it at 220 units. So we go ahead and say, we're going to say the price of this, if it's $1, we have a sunk cost of 220 units because we procured 220 units. It's $220 if we bought them at $1 a piece. So all the way across, no matter what we sell, we have the sunk cost of 220. The revenue on that item is, say, $1.50. So then you take $1.50 times 150 units, 160, 170, and there you go. You get the overall revenue. You'll notice in the green I have it highlighted here is you can't get more revenue than 220 because you procured it at this level. So the most you can receive is 220 times $1.50, which equals $330 total overall profit. And then down below, what you have is sort of the expected profit that you'll get sort of with the procured 220 units. To determine this across everything, sort of averaging out what may or may not happen, you got to take the profit times your probability. It's called the sum product, and that's an Excel formula, pretty easy to do. But what you would have to do to really model all of this is do that for every single instance. It just is very time consuming and would take a bit of time to sort of model everything out. And that's why this application is so powerful. It just automatically gets you to what the key demand that you should buy is and tells you what your overall profit would be based on that overall situation. And we do that through two sort of formulas, and it's called the critical fractal and the optimal Q. The inputs that you're putting into this is sort of your distribution, the sort of standard deviation that you have throughout things, what your purchase price is versus what you're going to cost you as far as your inputs, and then sort of what can you get if you salvage items. So say we buy a newspaper today, we don't sell it, maybe we could discount it at 50%, salvage some of that cost still. And then if we don't sell it, what's our penalty in overall cost? Lost customers, loss this, that's all variable that we'll have to just sort of understand our business and put that information in. And then of course, if we have delay, we can put our order in today, there might be a delay to actually receive the inputs. So factoring that in just to take into account some sort of inflation on how it impacts the overall value of each of these areas. The critical fractal is essentially a very simple formula. You figure out what your shortage cost is, and then you take your shortage plus your overage cost, and that gives you that percentage of that critical fractal, which is then used to plug into your optimal order quantity. I try to put on here some intuition around how you can think of the critical fractal. And it's really just a weight of, is it more important to be short, or there's this sort of duality and this tension in the overall problem that says shortage versus overage, which one's better to have? Obviously we want to meet all of our customers' demands, but also if profits your moving indicator, you could overstock yourself and have all this excess inventory, or you could understock yourself. So it's really a fine balance of that optimal value that you're trying to provide your overall customer. Then the optimal order quantity, since when we understand what probability we really should be trying to meet to, you plug that into your optimal order quantity, which tells you specifically how many units you should be ordering. So they kind of work in tandem together, and that's a very useful tool. And then finally, while those calculations give you the best case scenario, that's not reality. So we added a Monte Carlo, or I added a Monte Carlo simulation in here as well to sort of simulate events that may occur. So longer than lead time, so we don't get the items when we thought we were going to get them. We can't sell them if we don't have them. The ability for cost to change, the ability for demand to surge unexpectedly. And with those sort of scenarios, now you can take in the optimal solution, the modeled solution, and then determine what would be the best quantity to order for your given business. The application really helps you simulate all these different scenarios really quickly and drive to a given decision. So now we'll dive into what the actual application is, and with the knowledge here, how to actually use it. Now let's jump into the application. The application was built in PyCharm, hosted on GitHub, and then pushed to Streamlit to show so everybody can use the interactivity functions that was coded. This essentially, the left-hand bar allows you to collapse it or show it based on whether or not you want to provide inputs. The problem statement that we're using is very similar to what we were looking at earlier. Let's say our average demand for papers is 220 units. We sell them for $1.50 each, and it costs us $1 to procure it. Papers are time sensitive. So let's say, worst case, we can sell an old paper for 50 cents for whatever wasn't actually sold in a given period. And then a penalty if we don't have the inventory on hand, let's say it's 20 cents per customer, or per item per customer. It takes us, maybe we have to put our order in 5 days in advance, making sure that we receive our overall order. And let's just say we have a 2% inflation. It's going to sell right away after we receive the order. We package them and shoot them out. And then we're going to go ahead and go with the optimal Q, the economic solution that we were going through in the math earlier on how we calculate it. Remember the critical fractal, and then we calculated the optimal Q out of that same information. And then our standard deviation, let's say it can go 40 one way or the other, and we're trying to determine what the optimal solution is to purchase for these given items. We go ahead and run our simulation, and you can see that our overall profit should be $87 if we order 228 papers to meet the overall demand. Now that's not the entire story, because there's more to this as well, because we have the Monte Carlo portion too. You can sort of see the distribution here, and it's saying $99 is ideal to manage that overage cost and that underage cost. But you can, the probability is that we'll probably sell quite a bit more than that based on the simulations and the inputs to the simulations that we had. Let's go ahead and change that a bit and see how things sort of flush out It's not gonna change the optimal Q, but it'll change sort of that center graph and what the 5th versus 95th percentile may or may not be. So first of all, let's go ahead and simulate this more times. Let's say 32,000 different times. We'll roll a dice and see how these probabilities or these events play out within the Monte Carlo simulation. Our demand spike probability, let's say that there's a pretty good chance that something will happen. Maybe there's a big event that's going to happen and we think that demand will spike. There's a 40% chance that our demand will spike by twice what it is today. So that's going to definitely change the optimal solution. Our supplier is not going to be late, so there's no issues with that. They're always on time. So no concerns with that, but we can maybe give it a 5% chance. And then if at most it would be only 1 day in excess. And then our unit cost, maybe there's a rise in raw materials for paper. So potentially there's a 30% chance because the paper mill, the forest, they don't have raw materials, they can't produce the paper, and it's going to increase the overall price of end items. And then if that happens, at most it'll be 1.5% overall increase in overall cost. So taking all that into account, if we run our simulation, now what we can see is that there is still 228 that we should be ordering. Our profit has sort of reduced to $46 overall. And we can see at the Monte Carlo simulation what the odds are for the extremes on the left and the right side of the overall grouping of like how often we would receive $80 versus negative $40. So the key takeaway here is that your Monte Carlo simulation is going to show you the variance on sort of uncertain events that may or may not occur, and you're able to sort of model those in your overall program. Whereas the optimal Q is going to say how many items we should be ordering based on the most ideal situation. So we noticed that our profit went down up here. Why was that? Well, we put pricing differences. One, the cost for materials may go up, which then ultimately changes what our overall profit could be. But the optimal scenario is the optimal scenario. If I looked at this and I said $46 is what they're saying my optimal could be, I would probably, if I bought 228 units, looking at this overall chart, I might be more inclined to buy maybe 235 or 240 units and see what my profit would be in that case. It's going to open me to more risk, but at the end of the day, it might increase my bottom line. I do have a chance to lose money though if I do that. So it's all sort of a weighted game. So if we were to do a manual Q and sort of understand maybe a little bit more of what that risk is, and say we wanted to buy 240 units, we want to rerun our simulation. You can see potentially I might earn a little bit more profit, potentially not. Let's make this way high. At 400, you should see the profit go down, because now it's saying that there's a pretty good chance that we'll actually hold excess inventory if we did that manual Q. Just a neat tool to have in your toolkit, an interesting way to think through demand problems and sort of look at two different cases to do this news vendor problem. I found it to be interesting and was happy to sort of create the overall product to share sort of my skill set in critically thinking through a demand problem like this.